Hello everyone, my name is Sandhya Avasthi. I am assistant professor in ABES Engineering College, Ghaziabad. I am going to discuss topic KMP algorithm from subject design and analysis of algorithm. So in this video, I'm going to discuss introduction to Knuth Morris Pratt algorithm, steps in KMP algorithm, how to make prefix table, one example on KMP algorithm, and then discussion of time complexity. So KMP algorithm, it was conceived in 1974 by Donald Knuth and von Pratt, and independently by James H. Morris. So they all three together published it jointly in 1977. So the problem statement is basically given a string S, problem of string matching deals with finding whether a pattern P occurs in string S, and if P does occur, then return the position in S where P occurs. So Knuth-Morris-Pratt algorithm compares pattern P to text T left to right, but shift the pattern more intelligently than brute force algorithm. So in my earlier video, I discussed about naive string matching algorithm, whose complexity was order of n square in worst case when the length of pattern m is equal to n by 2. Because there it tries to match every time there is no match that takes place, it tries to find the match from the beginning. So the complexity is always, there are more comparison in that. But here in KMP algorithm, idea is to do the comparison, but intelligently. So we'll see how that takes place. So whenever a mismatch occurs, so what is the most we can shift? That is first identified. So that we can avoid redundant comparison. So it involves a very important step known as pre-processing step. And in this step, we try to find a prefix table. This prefix table is basically used as a reference to restart the matching of pattern characters with the text characters. So the main component basically in this KMP algorithm is calculation of a prefix table, also known as prefix function pi. So pi is for a pattern encapsulation, knowledge about how pattern matches against shift of itself. So it is used to avoid useless shift of pattern P, also avoids backtracking on string S. So another part is KMP matcher. So this is the part where string S, pattern P, and use of prefix function pi as input is done. So it tries to find occurrences of P in S by returning the value for number of shift S. So all the possible occurrences where the match is found, that value index or that shift value is returned. So let's see the example. Say a pattern P is given, A, B, C, D. So to build the prefix table, we first need to identify the prefixes and suffixes of a certain length. So here we see in this A, B, C, D, this pattern, the prefixes can be when try to take various sub-patterns from left to right, and suffixes are when we try to take different sub-patterns from right to left. Right, so proper prefixes in this pattern is A, which we see here, then AB, then ABC. So there are three prefix. We are not taking ABCD because that will not be a prefix. So for a pattern ABCD, prefix can be up to ABC. Proper suffixes can be D, then CD, then BCD. So we see D, CD, and BCD. So we can see when we compare both the prefixes of a certain length with the suffixes, we say there is no commonalities in both this. So the prefix table is built on this idea where we take sub-pattern from the pattern of different length, and we try to identify common values from both prefixes and suffixes. So let's take this example. And here we'll try to find out various shift where the pattern P is found there in this given text T. So the pattern here, we see the length of this pattern is basically the value for M is equal to 8 and the text size is 13. So we can see there are 3, 3, 3, 9 and 12 and one more 2, not 13, it's more than 13. So I'll just erase it. We'll see the values are basically how many characters we see 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14. There are 14 characters in it. So we'll take different sub-patterns from pattern P of various lengths. So we'll take a sub-pattern of length 1, then 2, then 3, then 4, then 5, 6, and 7. So sub-pattern is K and its length is 1. So proper prefixes and suffixes are none. So its value is 0. And then we choose a pattern, sub-pattern of length 2. So that means we choose KA. So if we take KA, so its prefix is K and its suffix is A. So that is written here. Prefix is K and suffix is A. And there is no common value from both prefix and suffix. So the value 0 is written. Same we do for a sub-pattern of length 3. So say the sub-pattern is KAY. So we'll write down all the proper prefixes. So the first prefix is K and then K. Also we would write all suffixes. So Y and AY. So when we compare both to find out longest common prefix, so we find none from here and here. So again, 0 is written. So the same we'll do for all the sub-pattern of length 4, 5, 6 and up to 7. And we'll complete this table. So after completing the same step for 4, 5 and 6, we can prepare our prefix table, something like this. So it shows the pattern and indexes of different values and the common of prefix and suffix. So longest common value of prefix and suffix. So we see for earlier size 1, 2 and 3, the values are 0. So that is written here. But when we take a sub-pattern of length 4, say I'm taking K, A, Y and K. So I will write down all the prefixes. So its prefix is KA, K, KA, KAY, N. Right? So there are 3 values. Also, I would write down all suffixes. So K, YK, and AYK. So here we'll see only K is common in both proper prefixes and suffixes. So I would call it longest common prefix. So its length K and the length of K is 1. So the 1 is written. Same we do with this pattern KAY, KA. So again KAY, K, and we would write down all the proper prefixes and suffixes. And the longest common prefix length is 2. That will come. You may check that. The same is repeated for here. So we'll get 3. And here we'll get 0. And at the end, we'll get 1. So this is our prefix table pi. And this will be used as a reference in matching step, KMP matcher algorithm. So now, as of now, the first step is prepared. That is, pre-processing has been done and we have made the pi table. Now we move to the next part. So this is our pattern, this is our text, and now pi table is prepared. So we start the very first step, the matching start similar to the matching that we used to do in naive strang matching. So it starts from index 0 from text. So let's see. The text is given. This is the length that the problem they have taken, and this is the pattern. So we'll start from the first character that is at index 0 and first character in pattern. So we see both matches. So we move to the next value. Again, this matches. So we move to the next value. And this also matches. We move to the next value. AA matches. We move to the next value. YY matches. Now, when it moves to the sixth character, the character at index 6th or 7th character K, so here this does not match and there is a mismatch. So mismatch takes place at position 6 of the pattern, but we see that already a sub pattern of 6 length in this is matched. So if we go by naive string matching algorithm, so you will have to do the same process repeatedly from here. So that will waste a lot of comparison. So that is saved here. So the redundant comparison is saved by looking that in this. So because this table gives the common prefixes, common of prefixes and suffixes and its length here. So we utilize that value to go back to the index in pattern. So we know that the sub pattern of length 6 matched and only there is mismatch here. So we'll just find out from where to start matching from the pattern. So the mismatch at position 6 of the pattern and the value at the position 6, that means this value, which is basically what? The 6th index is here, this, and its corresponding value is 3. So in the next step, we'll start matching from this value. So in the next step, the value at 6th index will be matched with value at 3rd index in pattern. Because at this value, at this point, the prefix table gives the value 3. So that is the idea. So there is no need to do the comparison because the longest common prefix in both the cases is KAY and here also KAY, which is a common. So that's saved. 3 comparison, it saves. Now the value at 6th index in text is compared with value at 3rd index in pattern. So again, this is matched. So this goes similar to any other matching algorithm. So now we move to the next value. So there is a match. So we move to the next value. There is a match. So we move to the next value. Now we see this does not match. So there is a mismatch at position 6 of the pattern, right? So we see there is a mismatch at position 6 of the pattern and the index here is 9. So what do? The longest common sub pattern that we see here is of length 6. We can see the longest common pattern here is of length 6. So we look up at the 6th value in the pattern, the pi table, right? So the length of matching sub pattern is 6. Now look up in prefix table at index 5. That is 1 less than 6. So the value we get is 3. So that means we'll match with the 3rd index. Again, so we'll match this with the 3rd index value in the next step. So in the 3rd step, we'll start matching from index 9 in the text and position 3 of the pattern. So the situation will be something like this. So this already matched and we have shifted. So it will match the value, the character at 9th index to the character at 3rd index in pattern. So we see that this is a match. Then this also is a match. It moves to the next value. This is a match. It moves to the next value. So this is a match. It moves to the next value. And this is also a match. So here we get our match. And at the end, the value that is returned is basically I minus m plus 1, which is the last index minus the length of the pattern plus 1. So we get the last index, the value for I is 13. So the value that we get is 13 minus 8 plus 1. So the only match that is found is exactly 1. We get only one answer here, where this entire pattern is matched with a sub pattern in the text, and the value is 6. So the value for shift is basically 6 that we get. So the running time of KMP is proportional to the time needed to read characters in the text and pattern. So as the time taken to create the partial match table, which is pi table, so we do that n times, so it is order of n, and time taken to search the pattern is order of n, right? So overall complexity is order of m plus 1, which is a linear time, and of course it is faster as compared to order of n square, which is the time complexity of knife string matching algorithm. So that's why KMP algorithm is a faster algorithm as compared to knife string matching algorithm. So the application of KMP algorithm is basically it can be used in application for plagiarism checking. It is used in DNA sequencing, and it is also used in checking word spelling. So the content for this PPT is taken from Introduction to Algorithm by Thomas H. Corman, and also from EdTech portal algotree.org. That will be all in this video. Bye bye everyone.